So in this video, we're going to take a look at word, skeleton, and balanced equations from a description on how to write those. So let's just take a look at this example over here, and then we'll do a few more together. But we have a solution of calcium hydroxide reacts with a solution of hydrochloric acid to form water and aqueous calcium chloride. Write a word equation for it. So first we find our reactants, and as you can see here, based on this question, calcium hydroxide reacts with hydrochloric acid. So these are reactants. They are the things that are reacting. So we write the calcium hydroxide and the hydrochloric acid on the left side, and we put an arrow afterwards. And our products would be what's formed. So to form water and calcium chloride. So as you can see here, we have calcium hydroxide, hydrochloric acid, and then we have our arrow there, and then our calcium chloride and our water there. They're all separated by pluses because they're separate substances, but reactants on the left, products on the right, and no states or aqueous or anything like that written out there, just strictly the names of the chemicals themselves. And that would be a word equation. You could take a skeleton equation, so you can make this as a skeleton equation, and you'd basically write it the same way you did before, except instead you would have the formulas written out. So calcium hydroxide figured out by the crisscross method, hydrochloric acid, the formula was determined because of the naming rules for acids, and then we said it would produce water, which is just H2O, and then calcium chloride over here, CaCl2, determined by the crisscross method. The states were found by the fact that acids and bases get AQ. CaCl2, we said it was aqueous calcium chloride. If I said solution, it would have been a solution as well. If I said solution, it would count as aqueous as well. And then also water, typically when it forms, it's in the form of a liquid. But if it's combustion, it might be in the form of a gas. So for combustion, we often have it in the form of a gas because combustion releases a lot of heat with it, and that causes it to evaporate. But in this case, it's in the form of a liquid. That's usually the case when you have a solution type of reaction happening, where most things are solutions. The water there is going to be in the form of a liquid. And then for the balance reactions, it's the same idea. You write it just like you did in the skeleton form, but then you have to go and you have to balance using the tips and techniques we learned in the previous video and in the reviews as well. So we'll do some practice problems writing each one of these types of reactions for different scenarios. Let's go to our handout to try those problems out. So here we go. We have magnesium metal and oxygen gas react to produce solid magnesium oxide. So the things that are reacting are my magnesium and oxygen gas. I don't need to write metal in there. It's just telling me that it's the metal that's reacting. If I go in the periodic table, I see that magnesium is solid, but I don't really care right now. All I care about is writing the name because I'm asked for a word equation first. So magnesium, and then it reacts with oxygen gas, so plus oxygen. You don't really put states. Some people will put states for those Hofbrinkel elements, but you don't need to. So plus oxygen, and then we get, it's producing magnesium oxide. And we don't have to put solid. We only have to put states when we're writing out our skeleton equation, magnesium oxide. And so we're going to write our skeleton equation next. We're going to turn these into their symbols and formulas. So magnesium is Mg, and in our periodic table, it's a black font, so it's going to be solid. And then plus, because that's right after magnesium, oxygen. Remember, oxygen is one of those Hofbrinkels. So we have to write it as O2, and oxygen in our periodic table is red font. So just to show you what I mean by the font again, in case you forgot, the font means like the color of the way it's typed here. So red for oxygen, and then black for magnesium over here. Okay. And we're told that we produce some magnesium oxide. And so to figure out magnesium oxide, I'm just going to do the crisscross. So Mg, because that's ionic, right? So that's a rule for naming that we learned before. Crisscross it like that, and we get Mg2O2. And don't forget to reduce. And so you get MgO. And then don't forget that in the question it told us it was solid. So that there is our skeleton equation for magnesium reacting with oxygen to produce magnesium oxide. This is a reaction where your teacher might have done it before. Your teacher may have burned some magnesium ribbon, and then you saw the bright light that was produced, and then the magnesium oxide was a white powder produced there as well. So that's that reaction that you just described there. And you can probably guess what type of reaction this is based on your grade 10 knowledge from before. Two things come together to make one. Synthesis reaction. Good. So we can try to balance this next. Just before we do that, though, a little reminder, the ones that would have a little to it there after them are the Hofbrinkel elements. Hofbrinkel, let's put N first, Brinkel elements. And remember, all of them are going to be, so H2, 2, 2, 2, 2, 2, 2. All of them are gas except for bromine, which is liquid, and then iodine, which is solid. But the rest are all gases, unless you're told otherwise. So that's a little reminder there. So for our balancing here, one more thing to mention as well. These are only twos if they're alone, like not in a compound. So in MgO, we don't have MgO2 there because to find MgO, we had to do the crisscross method to find the formula. So let's go ahead and write a balance equation. So MgS there. I'm just rewriting my skeleton, and I'm going to balance from my skeleton equation I did above. MgO. We can see our oxygens are off. We have 2 on the left and then 1 on the right. So I'll put a 2 here, and that'll give me 2 and 2. My oxygens are balanced. That's good, but I need to balance my magnesium, so I can put a 2 over here, a coefficient of 2, and that gives me 2 magnesiums. So now everything is balanced. I have 4 atoms total, 2 magnesiums, 2 magnesiums, 2 oxygens, 2 oxygens, and that's a balance equation that follows the law of conservation of mass. For example, if I had 5 grams of stuff here, I would have 5 grams of stuff here as well, providing I didn't spill anything or lose anything. So let's try another example. This is the one that we saw in your notes earlier, but we went through it quickly. So let's go ahead and try this one again. So we have a solution of calcium hydroxide reacts with a solution of hydrochloric acid to form water and aqueous calcium chloride. So let's do our word equation first. So what's reacting? Calcium hydroxide and hydrochloric acid, they are reacting together. So calcium hydroxide, no need to put solution, you can just write calcium hydroxide, plus hydrochloric acid, they've reacted and they're going to produce some calcium chloride, no need to put aqueous, plus water. And that there is our word equation. And so now we can do our skeleton equation. To do that, we need to find the formula for calcium hydroxide, which is CaOH2. I did that because of the crisscross method. Remember, it's an ionic compound like this. -1 for hydroxide, crisscross, and you get CaOH2. And don't forget, because it's a base, because of that OH there, and we're also told it's a solution, we put aqueous. Then for our hydrochloric acid, our naming rule is that this is a binary acid with H and Cl in it, so it's HCl, and since it's an acid, it's a solution, we put aqueous. And then for our calcium chloride, we do the crisscross and we get CaCl2, and we're told that that's a solution as well. Remember, if this is a solution, our water is not going to be a gas, it's going to be generally a liquid in that case. And usually we see that water would be a gas if it's a combustion reaction, but in this case it's a liquid. So that's our skeleton equation. Now we have to write a balanced equation that follows the law of conservation of mass. So when I write out my balanced equation, what I like to do is, and everyone has a different strategy here, but I'm going to rewrite my skeleton equation over here. Oops, arrow. Not equal, but arrow. CaCl2, aqueous, put those states back in there, plus H2O. Now, I'm not going to write H2O, I'm going to write HOH. And the reason I'm going to do that is because H2O and HOH are the same thing. But notice I have the polyatomic ion OH there and OH here. And I can treat them as sort of individual units. So I have two hydroxides on one side. So I'll get 2 hydroxides here. So that's 2 there when I put a 2 in the front, and 2 hydrogens. And so I need to get 2 hydrogens now, so I'll go ahead and put 2 over here on the left side, and I get 2 hydrogens, 2 chlorines. And I'm just going to go count everything. 1 calcium here, 2 chlorines, 1 calcium there. So it looks like both sides have balanced atoms at this point. I have 1 calcium, 2 hydroxides, 2 hydroxides, 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. Everything looks balanced. I'm just going to put a 1 in the front there, 1 in the front there, just to indicate that I'm completely done. And that there's our balanced reaction, balanced equation that follows the law of conservation of mass. So you should do some practice problems with writing out skeleton, word, and balanced equations. Make sure you know how to identify the states. There's a variety of practice problems that you can try on this page over here, and the answers are all included as you attempt them. I do want to go over a few more terms before we finish off, and it's just three more terms that that pertain to reactions. So when we talk about exothermic and endothermic reaction, that pertains to whether heat is absorbed or released by the reaction. So an exothermic reaction, think exit, is a reaction where after the reaction happens or while it's happening, energy is released. So if you were to touch the beaker or the flask or the test tube where that reaction is happening, the energy is being released to the environment, so it would feel actually hot to your hand. And generally, to represent an exothermic reaction, you write the heat term on the product side to say that heat's being produced, being released. So you write it on the product side on the right side. Now, there's another reaction called an endothermic reaction. And really, a whole bunch of different types of reactions can be described in this way. So your synthesis ones, decomposition, you can further classify them as either releasing heat or absorbing heat, for example. So endothermic reaction is the opposite of exothermic. Think endo, to come in, to enter. That's where there's an absorption of energy during a reaction. So it's absorbing energy, taking in energy from the environment. So if you touch the reaction that's endothermic, it's going to suck energy away from your hand, meaning that your hand's going to start to feel, if you're losing heat, cold. So an endothermic reaction feels cold. And to represent this in an equation, we put the heat term on the left side, on the reactant side, to show that energy is being absorbed by this reaction, and it will feel cold. So notice it's the opposite of exothermic. So if you remember exothermic, just remember endothermic is the opposite. That way it's a bit less to memorize. Lastly, there's something called a catalyst. So a catalyst is a substance that makes a reaction happen faster. You have catalysts in your body. You would call those catalysts in your body enzymes. There are many reactions in your body that will be very slow on their own, and you need them to happen fast if you want to survive. So enzymes in your body will help the reactions to happen faster. So that's essentially what a catalyst is. It's just a substance that helps a reaction happen faster. And the cool thing about the catalyst is it's not consumed itself. It's not one of the reactants. It can actually be reused. It's just there to help things along, basically to act like a coach. So it's speeding things up, but you can reuse it because it's not used up by the reaction. Usually for catalysts, you don't write them in the equation itself. You put them on top of the arrow. So this here is a reaction, a common one. That's the breakdown of hydrogen peroxide. So hydrogen peroxide, when it breaks down over time, it'll form water and then some oxygen. And so typically we have it as a liquid. Water would be a liquid here, and then the oxygen's a gas. And so this will break down slowly over time, but you can actually speed it up. You can speed it up in a few ways when you do this demonstration. What I want you to notice is that there's links to demonstrations there. So a link to an exothermic, link to an endothermic, and link to a catalyst reaction where you have a catalyst to speed something up. So I do want you to watch all these videos, especially the catalyst when it's very cool. But like I said, hydrogen peroxide on its own decomposes pretty slowly. But you can put in a catalyst to help break down the hydrogen peroxide. One example of a catalyst is the enzyme called catalase. And so notice that I put the catalase on top of the arrow there. The catalase is not a reactant, but it's just helping to speed things up. It might go and take hydrogen peroxide, maybe bend it a little bit so it can break apart a little bit faster. It might orient it in one way, in some way to make it faster. So you can throw catalyst into a bunch of different reactions. I could have probably thrown one in this reaction over here, for example, and tried to speed it up. And it might bring the reactants closer to each other so they could react faster, for example. A catalyst, we often may use it instead of heat. Because if we heat things up too much, it might, for example, damage our cells. So if we're using reactions in living things, we want to maybe use an enzyme rather than heat those living things up because it could damage them and hurt them. So those are just different scenarios where you might want to use a catalyst. So here, one other catalyst you could use is potassium iodide. So you could use a solution of potassium iodide, put that into the hydrogen peroxide, and it'll help the reaction happen a lot faster. It doesn't change the reaction whether I use a catalyst or not. The same products at the end are produced. It's just that with the catalyst it's faster, without the catalyst it's slower. Everything else though is the same. It's just it happens faster with catalyst. Again, write it on top of the arrow. It's not part of the reactants. It's not part of the products. It's its own thing. So at the end, I can recollect this and reuse it to speed up other reactions like that. And so those are some other pertinent, important terms for chemical reactions. Do make sure you know them and make sure you know how to represent a reaction. If I tell you it's exothermic, write it out the same way, but just make sure you put the heat term on the right side, the product side. If I say it's endothermic, write out the reaction like you normally would, but put the heat term on the left side, or the reactant side. And if I say there's a catalyst being used, just make sure you put the catalyst name on the arrow rather than as part of a reactant or a product.